we can think about a nearly infinite variety of possibilities. And our goal is to figure out the one or the ones that accurately reflect our own universe.
You got to question everything now. Truth has been compromised, man. You know what I mean? No matter what side of whatever you are on, truth has been seriously compromised because there's a counter opinion to everything.
Are we not risking too much with this dangerous discovery? The researchers at CERN have just uncovered a remarkable discovery, a breakthrough that could provide the answers to the most fundamental queries concerning human existence. But what they have discovered is much riskier than they could have ever imagined. Since its beginnings, the Large Hadron Collider has been used in multiple runs to assist scientists in unraveling many of the mysteries of the cosmos. However, something unexpected and unsettling was just recently found when they fired up the Large Hadron Collider with a new maximum beam of energy. Could it be an intergalactic signal? A message from the future, perhaps? Or something altogether different? Join us as we explore how scientists at CERN announced a chilling new discovery.
You're watching Decode.
The LHC is a particle accelerator, a machine that carefully increases the energy of subatomic particles so that researchers may examine the interactions that follow. Even though they are challenging to construct, these colliders achieve a far greater center of mass energy than fixed target configurations, making them exceptionally powerful research tools in particle physics. The outcomes of these collisions can then be studied by scientists to gain knowledge about the subatomic world's structure and the underlying laws that govern it. It is hard to investigate many of the byproducts in any other way because they are only created by high-energy collisions and decay in incredibly short times. The Large Hadron Collider is located 50 to 175 meters below in a circular tunnel. This depth variation was designed to eliminate the need for the development of a vertical access shaft beneath the Dura Mountains by limiting the quantity of tunnels there. In order to avoid having to invest significant sums of money in a pricey neighboring land, this tunnel was chosen by CERN. The crust of the Earth also provided shielding against background radiation. Between 1983 and 1988, the 3.8-meter-wide concrete lines tunnel was constructed. It once served as the location of the enormous electron-positron collider. 4 times, with the majority of its length in France, this tunnel spans the border between Switzerland and France. Ancillary equipment like compressors, ventilation systems, control systems, and refrigeration plants are housed in the above-ground structure. It was calculated that the LHC and LHC-related simulations produced about 15 petabytes of data annually. To manage the enormous volumes of data produced by the LHC's collisions, the computing grid was built as part of the machine. Using a grid-based computer network design, it is a collaborative international effort. The cost of building the Large Hadron Colliders was roughly 7.5 billion euros, one of the most expensive scientific experiments ever constructed. A budget of $2.6 billion, plus an additional $210 million for trials, was approved for its construction in 1995. After the LHC began operating on September 10, 2008, a magnet quench incident that seriously damaged more than 50 superconducting magnets, their mountings, and the vacuum pipe caused the LHC's initial testing to be postponed for 14 months. During its initial operation from 2010 to 2013, the LHC smashed 2 opposing particle beams of protons up to 4 tera-electron volts or lead nuclei. During the first run of the LHC, the Higgs boson, a number of composite particles including the Betonium state, and the first generation of quark-gluon plasma were found. The Higgs boson, an essential component of the standard model of physics, predicted by theory but previously undetected because of its massive mass and elusive nature, was the initial goal of the Large Hadron Collider. CERN physicists projected that the LHC would produce a large number of Higgs bosons each minute if the standard model was accurate. This would enable physicists to definitively affirm or deny the existence of the Higgs boson. In addition, the search for supersymmetric particles particles and other speculative particles was made possible by the Large Hadron Collider. The first operational run began after the initial testing in 2008 and lasted until 2013. Thereafter, a lengthy shutdown for modifications continued until 2015. The second operational period was from 2015 to 2018, and it was followed by another lengthy interruption until 2022. With a beam energy of 6.8 tera-electron volts, the LHC reopened in April 2022. The predicted duration of this cycle is 2026. When a breach appeared in the Earth's magnetic field on July 7th, during the third run of the Large Hadron Collider, physicists were baffled. This strange crack didn't appear in a split second or with a flash of lightning. The Earth's magnetic field actually separated for 14 hours. Strong solar winds were able to pour through the gap, resulting in significant geomagnetic storms and some incredibly compelling aurora. We were unable to take our eyes off the aurora produced by the geomagnetic storm brought on by this crack. However, how did this crack develop? In fact, a co-rotating interaction zone from the Sun, or CIR, was what brought about this break in the magnetic field. These CIRs are actually large-scale plasma structures that emerge when fast-moving and slow-moving streams of solar wind meet in the low and intermediate latitudes of the heliosphere. The solar magnetic field and solar winds are located in the heliosphere, which encircles the Sun. The co-rotating interaction zones, such as coronal mass ejections, CMEs, which are launched from the Sun towards the Earth, can contain shock waves in compressed magnetic fields, resulting in turbulent space weather, which we typically witness as a stunning aurora. This one caused a long-lasting G1 class geomagnetic storm when it slammed with the Earth's magnet in the early morning hours of July 7th last year. According to researchers at the National Oceanic and Atmospheric Administration, a coronal mass ejection was embedded in the solar wind before the co-rotating interaction region. Do we need to be concerned about this crack? Experts claim that there is nothing to worry about because cracks in the Earth's magnetic field occur frequently. We are protected from solar storms by the Sun's magnetic field, which serves as a shield. Although it is believed that the different fissures in the field open and close fairly quickly, these most recent cracks have shown that they can stay open for several hours at a time. The couch is destroyed, but the house blocks out much of the storm. Similar to this, while our magnetic shield withstands the majority of space storms, occasionally enough energy manages to get past its defenses and interfere with power systems, radio communications, and satellites. Fortunately, this fracture in the magnetic field did not result in any power or radio blackouts. On the other hand, citizens of Canada and the United States were treated to some breathtaking northern lights. Scientists have also found that the Sun is unusually active considerably sooner than expected and is about to enter its most active phase in the solar cycle. This suggests that over the next 3 years, your odds of viewing an aurora, which is currently good, will only increase. The Large Hadron Collider has lately found other things in addition to this hole in the Earth's magnetic field. In July 2017, a number of analyses based on the enormous data set obtained in 2016 were made available. The characteristics of the Higgs boson were investigated more thoroughly, and several other findings were made with better accuracy. In data gathered from the collider's first 2 runs, the LHC collision experiments have found about 59 additional hadrons since March 2021. On July 5, 2022, it was announced that research on the decays of charged B mesons had led to the discovery of a novel type of pentaquark made up of charm quarks, charm antiquarks, up, down, and strange quarks. On the other hand, CERN is also the site of a number of non-LHC dark matter experiments, such as CAST and A64, which collide electron beams with atomic nuclei and look for hypothetical particles called axions, and AMS, which monitors the International Space Station for cosmic rays. A significant fraction of the cosmos is assumed to be made up of dark matter, a hypothetical kind of stuff. Because it does not emit, absorb, or reflect light, it is called dark, and and cannot be directly detected using a telescope or other electromagnetic radiation detecting equipment. However, its gravitational effects on observable matter, such as stars from galaxies, can be used to infer its presence. According to estimates, dark matter makes up about 85% of the universe's mass, and that many well-known phenomena, such as the galactic rotation rates and the distribution of stuff on a cosmic scale, can only be explained by its presence. Thanks to a precise experiment carried out at the Albert Einstein Center for Fundamental Physics at the University of Bern, in collaboration with CERN, an international research team recently succeeded in drastically restricting the scope for the occurrence of dark matter. Dark matter's real composition is still a complete mystery. There is no doubt that it is not made up of the same materials as the stars, planet Earth, or humanity. Around the world, increasingly sensitive tests and approaches are being used to look for possible dark matter particles, but so far without success. Axions are a theorized class of fundamental particles that make a good contender for dark matter particles. These incredibly light particles have the potential to explain other critical particle physics events that are currently unknown, which is a big advantage. If the elusive axions exist, they ought to leave a recognizable mark on the measurement tool. The experimental exclusion of as yet unknown parameter space of axions was made possible by measurements done in conjunction with French researchers at the European Research Neutron Source at the Institut Lohr-Langevin and CERN. As compared to past testing, it was also shown that it was possible to look for fictitious axions that were more than 1,000 times heavier.
Thanks for watching. Subscribe for more.